presentation, I want to talk about the effect of interference on path performance and fade margin degradation in particular. I'll start by introducing myself. My name is Rod Walker. I have an electrical engineering degree from McGill University in Montreal. I have 27 years of microwave system design experience, primarily with a major telecommunications equipment manufacturer, designing customer microwave systems, but also working with equipment designers and with manufacturing. Subsequently, I worked, and I'm still working, 17 years as a consultant slash contractor, providing microwave system engineering design support and developing customized software applications, primarily for microwave system designs. Okay, so the effect of interference on path performance. I have a little drawing here that shows you an interfering signal coming off another link, getting into my victim receiver. And the process that happens is that the interference gets into the receiver, which causes additional noise in the receiver. So the composite noise in the receiver rises. The result of that is that the fade margin is reduced and the availability decreases, which is ultimately what we're concerned about. This presentation will talk about primarily the two midpoints, how the noise from interference adds into the noise in the receiver, and then what that does to fade margin, how we calculate that, what's the impact. So that's our focus here. I'm not going to spend time talking about how to calculate interference, through antenna discriminations, etc. Nor am I going to talk about availability calculations. Now, software tools like path loss do this for you, and they do it very well. However, in my experience, understanding the mechanism behind this is really invaluable, primarily in terms of troubleshooting, but also in just validating what the software is telling you, that it makes sense, and understanding what's going on. It's really important. Now, a small warning, in this presentation there's some simple math used, just a fair bit of it, but it's not complicated, and it is really fundamental to understanding. I'll start with fade margin in this slide here. I'm showing four modulations from 1024 down to 128 and what their thresholds are on the left here. These are the numbers that came out of the manufacturer's data file, and it's in particular it's an iPasso radio. Now, I'm showing also at the top here a minus 30 dBm received signal level. That's particular to whatever the link design is, but we'll use this in our example as minus 30. So the fade margin is the distance in decibels between the nominal received signal level, unfaded received signal level, and the threshold. So for the 128 QAM, the distance is 37 dB in this example, basically from minus 30 to minus 67 dB or dBm. And basically you can do the same math for the others and get the other numbers that are shown here for fade margin. So it's how much the nominal signal can decrease by fading before we start to have problems with the performance of the radio. And these thresholds in particular were chosen for 10 to the minus 6 bit error rate. Now the thresholds are again shown in this next slide. However, what I want to point out here, which is really critical, is that there is noise in the receiver already. There's basic noise caused by electron movement and so on. If you want to learn about that, you can go read Boltzmann and Boltzmann's constant, probably on Wikipedia or in physics books. So the thresholds are a given number of decibels above the noise, the ambient noise in the receiver. So for the 128 QAM, it's 24.6 dB above the noise floor of minus 91.6. And so all the way down to 1024, which is 34.1 dB above the noise in the receiver, and it gives a threshold of minus 57.5. Now, what's really critical in our discussions here is that this signal to noise ratio requirement is fixed. Whatever the noise is, the signal has to be that number of decibels above it, and that's so the manufacturer has given you his threshold numbers based upon the ambient noise in the receiver with no interference and no other impacts coming into the receiver. So that's what it requires for it to operate properly. And as I said earlier, these threshold numbers are the numbers, the lowest numbers of incoming signal that you're allowed in order to achieve a bit error rate of 10 to the minus 6 or better. So I put these two slides together here because when we talk about interference getting into the radio, it gives you a good visualization of what the impact is. So again, we have the noise at the bottom, minus 91.6, we have the thresholds in the center, and we have our received signal level. I'm showing you the signal to noise ratio requirements here and the fade margin at the top. So what's fixed in here is the received signal level. That's a calculated level based upon the design of the link. And the SNR requirements, they're fixed. They're part of the definition of how the radio works. So if the noise floor rises because we've added additional noise from interference, for example, these arrows here are also going to rise, which means that the thresholds have to go up in order to maintain this 24.6 up to 34.1 signal to noise ratio. So as a result, what that means is that the thresholds go up, the received signal level is fixed, so the fade margin gets squeezed. Basically, it gets reduced. So I'll show you in a moment how that works, but this is the fundamental idea behind the degradation of fade margin by adding interference. Now, in this slide, I'm showing you an example of receiver noise at minus 91.6. That's this red line here. With an interference level, I chose at minus 93 dBm. When you add them together, the composite result rises to minus 89.2, which is a 2.4 dB rise in the total noise within the receiver, and that's going to translate into a 2.4 dB squeezing of the fade margin, basically reduction of the fade margin. So what I want to talk about next, of course, is, well, how do we do this calculation? How do I go from taking these two numbers to get this number and work out the 2.4? But before we actually do those calculations, I thought I would show you a slide here with the degradation shown. So the noise rises as it shows here. As a result, we have higher thresholds and reduced fade margins, as I just said. So in the case, for example, of this 128 QAM, the fade margin was 37 and it's risen up to, or decreased rather, to 34.6. It got squeezed. Okay, before we talk about calculations, we need to talk about units. So we in this industry, we always talk about dBs and dBms and basically doing our calculations. Now, a dB is not a real number. It's a logarithm of a real number. A real number is a real physical power, and that's measured in watts or milliwatts or a number of other units. But it is something that is physically real. You can bring it down to basic physics. dBm is a transformation of a milliwatt into a decibel form, basically a logarithmic form. And the reason we do that is so that if we were working in real world units, so an amplifier might have a gain of 10 and then there might be some loss through some cable of 50%. If you're going to work those out in terms of watts, milliwatts power going through, you have to multiply things through. That's can be a lot of work, especially with complicated systems. But if you convert everything into a logarithmic form, in other words, a dB form, then doing the math is just simply adding and subtracting. It's much, much simpler. So dBs and dBms were adopted many years ago in this industry as a much simpler way to work. So there's two formulas that I'm showing you here to go back and forth. So if you have milliwatts, you just take 10 times the log of that to get dBm. And if you have dBm, you just do 10 to the power of that dBm over 10 to go back to milliwatts. And that's, we're going to use this a lot. So let me just show you in a spreadsheet. Okay, in the top box on this spreadsheet here, I have an example with minus 93 dBm, calculating into milliwatts using that little formula, and then back to dBm using the reverse formula. Very, very simple and very useful. Okay, so when we add interference to the noise floor in a receiver, to do that addition, we have to do it in real world units, which is milliwatts in our case. So I'm giving you an example here where I have two interferers, one of which is minus 93 dBm, one is minus 97 dBm, and with the receiver noise of minus 91.6. these three are converted through these formulas into milliwatts, same simple formulas at the top. We then add them up because now they're in real world units. We can sum them up, and then we convert them back into dBMs because we work in dBMs using this 10 times log of the number formula. So the ultimate result in this particular example is the noise in the receiver originally was 91.6, minus 91.6. We added in a couple of interferers, and the noise, the total composite noise in the receiver has risen to minus 88.6. So we've significantly degraded or added to the noise, which has raised the thresholds in the receiver, and that's squeezed the fade margin. And the amount that it squeezed is the difference between the original noise and the new composite noise. Now I can show you actually this little calculation in the spreadsheet as well. So in the center box of this spreadsheet here, I show you these two interferers with the noise converted into milliwatts using the formula shown, summed up, and then converted back to decibels using the log formula. So this is a pretty straightforward little calculation. Okay, so fade margin degradation. As I just said, the fade margin gets squeezed. So the definition of fade margin degradation is the fade margin without interference minus the fade margin with interference. Normally is a positive number. So basically do that difference and figure it out as a positive number. So that would be the end of my discussion if I could be sure that you knew what the receiver noise floor is. But manufacturers don't generally publish noise floors anymore, although they did in the past. So we have to figure out what the noise floor is in order to figure out that degradation number, which is what we're fundamentally after. We can do that using specifications that they give us, which allow us to do that calculation. So the T to I spec is the most important specification for this, as well as the threshold at which that T to I spec is defined. So T to I is defined as the number of decibels that the interference level must be below the threshold, such that when it adds into the receiver, the threshold rises by 1 dB. So it is if you know the received signal level, received threshold number, you subtract out the T to I number, that'll give you that interference level, which causes a 1 dB degradation for the threshold. And this is all defined at 10 to the minus 6 bit error rate. So in this line over here, you can see the simple calculation. The interference is received threshold minus T to I. Now, that gives us an interference level, but doesn't give us a noise floor. So we want to find the noise floor. There's two methods. So I'm going to show you first the slightly more complicated method because it gives you a much better insight into the mechanisms of what's going on. But there is a simple formula which I'll show you afterwards. But understanding, I think, is really important, which is why I'll talk about what I call the iterative method first. If you assume a given noise floor, say a minus 100 dBm, and you add the interference level based upon this T to I value, which we've just shown how it's calculated here. If you add those and the noise floor, the resultant composite noise floor is 1 dB greater than the original noise floor, then you'll have chosen the right noise floor initially. My minus 100 I chose. If it came out to be a 1 dB difference in the total, then that's my noise floor. Of course, the chances of you picking the right noise floor initially are pretty low, but you can put it into a spreadsheet and adjust the noise floor assumption, the input, until you get that 1 dB result, and then you know you've got the right answers. Basically an iterative process. So let me show you that in the spreadsheet. Okay, in this spreadsheet, I've got a threshold of minus 57.5 and a T to I specification from the manufacturer of 40. I'll show you where these two numbers came from in a moment. Based upon the T to I definition, the interference is then going to be the threshold minus the T to I, which gives me minus 97.5. This is the interference level which should cause a 1 dB degradation. Now, I'm going to assume initially minus 100 dBm noise floor, and then I'm going to add the interference to the noise using the method that I showed you earlier. So the interference is converted into milliwatts here. The noise is converted into milliwatts here. Again, those simple formulas. They're summed up, and then they're converted back into dBm. And this is my new composite noise floor. So in my original thought here, I was using minus 100. It's risen to minus 95.6. The difference is 4.4. So that's obviously wrong because I'm looking for 1 dB degradation, not 4.4, which because the interference level is based upon a 1 dB degradation. And we know that these numbers are correct. The threshold and TI are correct, so the interference is correct. So the only thing that can be wrong then, of course, is the noise floor. So I can play with the noise floor to find the number that gives me 1 dB here. So if I go say minus 97, it takes it to 2.8. Now XL, which I'm working in here, has some iterative functions to solve, but I'll just let you look that up for now, and I'll just put in the answer here. So it comes out to minus 91.6 is the noise floor, and as you can see, it gives me a 1 dB degradation in the noise floor and ultimately the thresholds. So minus 91.6 is the answer using an iterative method, just by playing with the noise floor to get the right answer. Okay, so going back here at the very bottom of this slide, I show you the formula method, which you probably use because it's simpler. But as I say, now that you've understood this, you'll have a good understanding of what's going on. So the formula basically says the noise floor is the received threshold minus the T to I plus an offset of 5.868. Let me show you that in the spreadsheet. Okay, so here I have a simple spreadsheet calculation. The threshold is here, T to I is here, this offset that I talked about is here, and this is the calculation, which gives me exactly the same result I got through my iteration method. Okay, so the next thing I want to show you is where these numbers came from. Where do you find the threshold and the T to I? You can, of course, find those in radio documentation, specification sheets. I'll show you in path loss because this is where I extracted it. So looking at this path loss link, I'll go into the radio specifications and slide down to the receiver data here, which is here. So all this area here is receiver data. You can see that for the threshold at 10 to the minus 6, everything we're doing is 10 to the minus 6. It shows me that the threshold value is minus 57.5, which is the number I've been using. And down below here, I can see the T to I ratio of 40. So that's where these two numbers came from. What this doesn't show you actually is what the modulation level is for this particular threshold. Because this is an adaptive modulation radio, there's many thresholds. But I can get to that through their thresholds, through their adaptive modulation table. If I look for minus 57.5, let me just open this here. So under 10 to the minus 6 bit error rate threshold, minus 57.5 is here. It tells me that it's a 1024 QAM radio. So that's a good thing to know. You also notice, of course, that there's a lot of different thresholds, and we'll use that in a spreadsheet in a moment. Okay, so in this spreadsheet here, I've basically shown you all the modulations that were in that table with their thresholds, and I'm also showing the noise floor, because the noise floor is constant across all modulations, and this was the one that we just calculated. And for this exercise, I'm just assuming an interference level of minus 93, and because the interference level is, again, is constant independent of the modulation, I just put it into all of them. And going through the same sums of interference and noise, down below here we have total noise with interference for the cases, and you can see they're all identical. What that means is, of course, that the noise floor has moved identically, independently of the modulation, and in this again in this example, it's 2.4 dB. So that's kind of an important result to understand, is that interference degradation of fade margin is independent of modulation. Okay, so in summary, just go back quickly through the slides here very rapidly. I showed you a definition of the fade margin here. I showed you the signal to noise ratio requirements and the basic receiver noise and how everything relates. And then I showed you how adding interference into the radio raises the noise floor, raises the threshold and squeeze the fade margin. So essentially they're reduced by the amount that the noise rose. So that's really all there is to it. The only complication to all of this, of course, is finding the noise floor, but there's a fairly straightforward way to do that. So I hope this was easy to understand, and thank you very much.